All right, this video is a quick AP Stats test review to cover sampling distributions. Sampling distributions really is the beginning of everything we learned about inference. It's a pretty important topic. So make sure that you understand exactly what a sampling distribution is. A sampling distribution is a model of what all possible values of a sample statistic could be of a certain sample size drawn from the same population. A sampling distribution is not a picture of individual values. It is the mean or the proportion of a sample size of n. So sampling distribution, I tell kids, a sample shows individual values within a sample. A sampling distribution shows sample after sample after sample after sample after sample, because when you put ing at the end of a word like jump, it means to keep jumping. Start jumping and keep jumping over and over again. And that's what sampling distributions are. They're showing a sample after sample after sample. They're not showing one individual sample. They're showing all possible samples. Now, there's a couple rules that we have to learn real quick when we deal with these sampling distributions. And the first rule is that when you select a sample, you got to do it randomly. So the center of your sampling distribution will be the true population parameter, mean or proportion, as long as the samples are selected randomly. The second condition is that the samples will certainly vary as long as they are independent, which may not be true, but we can assume as long as the sample size is less than 10% of the population, there will be independence. Now, this is a tricky condition that a lot of kids just kind of remember, but the idea behind it actually makes a lot of sense. Typically, when we sample people, we do not use replacement, which means after I select Kelly to be a part of my sample, I don't put her back to sample again. I sample without replacement, which means that every time you take somebody out of the population, the probability of getting another person the probabilities are slowly changing basically. But the idea is as long as you take out under 10% of the population, even if you don't replace, that small change is negligible, okay? If you think about there being 100,000 people in a big population, if you take one person out, okay, now there's not 100,000 people left, there's only 99,999. Well, that's not a big change, and that's why we make sure that we say as long as your sample, is under 10% of the population, that small change is a negligible one that we don't worry about, so we still have independence from sample to sample. All right, now the last one is the shape. The shape of a sampling distribution will be normal provided that that sample is big enough. And we're going to talk a little bit more about that one for depending on proportions or means. All right, so let's just dive into talking about sampling with proportions. Okay? All right, so if I'm going to look for, say, the proportion of people that have blue eyes, and I'm going to look at a sample of size 50. And I want this to be from U.S. adults. That's my population. All right, so if I take out a sample, I'm going to get a sample proportion. Maybe I get something like 12% have blue eyes. Then I could take out another sample, another sample, another sample, because that's what sampling is, taking out a whole bunch of samples. And not every sample is going to be the same. Right? They're going to vary. Some samples are going to be more, some samples are going to be less. They're going to vary a little bit. So if I take all these samples and make a picture of it, okay, well, that is a very poor straight line. I have a hard time drawing straight lines. Okay, so if I take a picture of this, right, if I start to kind of say, okay, well, my first sample was at 12%, so I'm going to put a p hat right there, or maybe put a dot right there at 12%. But another sample was at 13%, and another sample was at 14%, but you know what, another sample was at 11%. The idea is that when you keep sampling, they're going to start to stack up. Maybe there's another one right here, and another one right here, and another one right here, and another sample right here, another sample right here. And what we know about sampling distributions, when you keep sampling, very few samples are going to be extremely high, very few samples are going to be extremely low, and you know what most samples are going to look like? They're going to look like the normal model. Sorry, that's a really bad normal model. But the idea is that if you look at all possible samples of size 50 drawn from the United States adults, the average, right, the mean of all those samples is going to be the truth. If I take the mean of all those samples, There's going to be a very few high ones, very few low ones. They're going to really start to stack up around the truth. The true proportion of people with blue eyes in the United States is going to be the average or the mean of all of those samples, and that's going to be smack dab in the center as long as those samples were random. Now, we also need to understand how these samples are going to deviate, right? Because they do. They vary. They deviate. Some are a little higher, some a little bit lower. So there is a standard deviation of all those samples as well. And the formula for that is one you should know by now. P times 1 minus P divided by your sample size. Now, the fact you're dividing by your sample size emphasizes a really important point. Bigger samples vary less. So the bigger your samples are, the closer those samples will be to the truth because they're bigger, hence you will vary less. So that's it, guys. The average of all those p hats is going to be the true p. The standard deviation of all those p hats is going to be that simple formula. Now, how do I know I'm allowed to use this formula for standard deviation? Well, I have to have independence, and that's why we check that under 10% condition. And the other thing is I want to make sure that I could use this normal model. I mean, the normal model is such a great model to use, but I do need to be big enough. So how do I know I'm big enough? Well, you need 10 or more successes and failures. So if I'm looking for people with blue eyes, that's considered a success. So in these samples, I need 10 or more people to have blue eyes, and I need 10 or more people to not have blue eyes in every sample for this sampling distribution to work out. And guys, it's really that simple. It's such a great, easy model to work with. So let's just do a quick example. Let's just say that we know that 13% of adults are left-handed. That's the truth. We know it, right? And we're going to look at samples of size 75. Okay, well, the first condition is those samples better be random. The second condition is, well, 75 needs to be under 10% of all adults, and I'm pretty confident in that statement, that 75 is under 10% of all adults. But as it currently stands, if I have 75 people and 13% are supposed to be left-handed, that's only 9.75 successes, and that's not enough to use the normal model. I do need to be 10 or more. So that is a good idea to make sure you always think about those conditions. So let's use 125 people. Now, 125 needs to be random. I'm pretty sure 125 is still under 10% of all people. And when I multiply by 13%, now I do get 16.25, which is enough successes. Now, of those 125 people, I also need to have 87% be not left-handed, right? Those are my failures. So 125 times 0.87 is clearly going to be more than 10. It's 108.75. I just need both those big numbers bigger than 10 so that I could draw the model. And the model is really easy to draw. I'm going to draw a normal model. Right smack dab in the middle is going to be the truth, 13%. Now, is every sample going to come back 13%? Nope. In fact, 50% going to come back higher and 50% going to come back lower because it deviates. So I expect the average of all those samples to be 0.13. I don't expect every sample to be 0.13, but I expect the average of them all to be. And there is going to be some deviation, right? That's what the normal model shows me. Some samples will be a little bit higher, some samples will be a little bit lower. To figure that out, I'm going to use the square root of 0.13 times 0.87, that's 1 minus p, divided by my sample size of 125. So that's 0.13 times 0.87 divided by 125, just using my calculator here, and I get 0.0300. Sorry, 0.0300. That's a really nice number to work with. What that means is that samples could be 16%, 19%, or even 22%. I'm just going up 3, up 3, up 3. Could go down 3, 10%, down 3, 7%, down 3, 4%. So very few samples should come back 22% or more left-handed. That would be very weird. And at the same time, very few samples will come back under 4%. Most samples are going to come back somewhere between 10 and 16%. Because remember, that's where 68% of samples fall. Now, the other thing we can do once we have all this model drawn is we can answer probability questions, right? And everybody hates probability questions, but they're really easy once you have this model. Now, I could say, hey, what's the probability that a sample comes back greater than 20%? What's the probability a sample comes back greater than 20%? All right, well, 20% falls somewhere right around here, right? And I want to find the probability a sample is more than that. So I'm already getting the idea that it's probably going to be unlikely. But since it follows a normal model, I could use normal CDF to answer this question. I just need the z-score first, because remember, to use normal CDF, you need the z-score. So where does 20% fall in terms of this model? Well, I'm going to subtract the center, 0.13. I'm going to divide by the standard deviation, 0.03, and I'm going to get my z-score. So 0.2 minus 0.13 divided by 0.03. Oop, I did some math wrong on my calculator, sorry. And I get 2.33333. 2.3333. I'm having a hard time writing that. And again, that actually makes sense because here's one standard deviation, here's two standard deviations, and it's a little bit more than 2. All right, so now I'm just going to go to grab my calculator here. I'm going to go to normal CDF, which is number 2 there under a second vars. I'm going to look above, so that means I'm going to start at 2.3333. And then my upper value is going to be infinity because I want to go way up to 99999. Now remember, I don't have an infinity button, so that's why we just use a bunch of 9s there. And bingo! Very, very, very small proportion of samples are actually going to be bigger than 20%. It's actually 0.0098. Very, very, very small. So it would be very unlikely, in fact, it would be very significant if a sample did come back 20%. So if one of these samples, now remember this sampling distribution is filled with billions of samples, but if one of them came back 20% or higher, I would be pretty shocked. Actually, that'd be pretty unlikely. That'd be pretty significant. All right, and that's it for proportions. Let's move on and talk about means now. All right, let's say that we want to find the average length of a fish in Lake Erie. Well, let's say that we know the average length. Maybe scientists have told us that the mean length of fish in Lake Erie is 10 inches long. That is the mean length of a fish in Lake Erie. But, you know, every individual fish in Lake Erie does deviate. So the standard deviation for a single fish in Lake Erie is 2.3 inches. Okay, great. Awesome information. All right, now, what about a sample? Because I want to take a sample, and I want to get a sample mean. And I want to take a sample of 50 fish. And if I take a sample of 50 fish, I'm going to get a sample mean, X bar. Now, am I going to always get 10 inches? Probably not. Why? Because samples vary. So this sample does need to be random, so that has to be true. There's a lot of fish in Lake Erie, so I think the second condition is also true, that 50 is under 10% of all fish in Lake Erie, so we have independence. Because I'm not going to replace these fish. I guess that's kind of mean. Maybe I should replace the fish because it would be mean to hurt the fish. But anyway, I digress. And the last condition is I need to be big enough. Now, this is the tricky condition here because there's a lot going on with means. Now, technically, any sample is big enough if your population is already normal. So if I knew that the population of all fish in Lake Erie was normal, technically any sample size would be big enough. But if I don't know the population, for example, in this case right now, I mean, maybe the fish in Lake Erie are skewed. I don't really know. Well, that's okay because we have central limit theorem. The central limit theorem is a very important theorem that says, hey, as long as your samples are 30 or larger, even if the population is unknown or non-normal, the sampling distribution will still be normal. So this is awesome. So as long as my sample size is 30 or larger, the central limit theorem tells me that the sampling distribution is big enough to be normal. So that third condition checks out there. All right, so now all I got to do is think. Since I checked all my conditions, I can draw a very pretty little picture. All right, if I go and get a sample of 50 fish, I certainly expect to get 10 inches. Why? Because that's the truth. So that's exactly what I expect, right? I would expect the mean of all those means to be 10 inches, right? I mean, this sampling distribution is not just one sample, it's all possible samples of size 50. There's tons of X bars floating around in this thing. Most of them are probably going to be close to 10. Some might be a little higher, some might be a little lower. But again, the average of all of them, since some are below and some are above, the average of all of them will be 10. All right, but what about the standard deviation of the sampling distribution? Well, this right here is the standard deviation for the population, which means any one fish could deviate by 2.3 inches, because fish deviate a lot. I mean, that's one fish. But we're no longer talking about one fish. We're now talking about 50 fish. So the formula is actually quite easy. You just take the standard deviation of the population and you divide it by the square root of your sample size, n. So all I'm going to do is take 2.3, I'm going to divide it by the square root of 50, and I'm going to get the standard deviation for my sampling distribution. And that confuses a lot of kids, so let me just try to go through that one more time. One fish could deviate by 2.3 inches. By the way, this is 0.33 inches. That's what I got there. Now, one fish could deviate by 2.3 inches. But again, we're no longer talking about one fish, right? We're talking about 50 fish. And if I do have one small fish, I probably have a big fish to even things out. That's why bigger samples vary less, a very common theme in this class. So a bigger sample, a sample of size 50, on average should vary much less than a single fish, which is why you divide by the square root of 50, and we get that a single sample, a sample of 50, will deviate by 0.33 inches. So this is going to be 10.33, 10.66, and then 10.99, going down, down, down. 10 go down 0.33 is going to be 9.67. Go down 0.33 is going to be 9.34. Go down 0.33 is going to be 9.01. Now, if I made my sample size bigger, I would have an even smaller standard deviation. Or vice versa, if I made my sample smaller, I would have a bigger standard deviation. So bigger samples vary less. So yes, the truth is 10 inches, but not every sample is going to come back 10 inches. Some samples might come back at 10.33 inches. Some might come back around 9.67 inches. And that's the idea of what a sampling distribution shows us. It shows us what all possible samples will look like. And again, we could also incorporate probability questions here. I could say, hey, what's the probability that a sample comes back under 9.5 inches? What is the probability a sample comes back under 9.5 inches? Okay, well, here's 9.67. Here's 9.34. 9.5 is probably right around here somewhere. So I want to find the probability a sample comes back lower than that. Well, again, because it follows a normal model, I want to use the normal model. So I do need to use normal CDF. All I got to do is calculate a z-score. I'm trying to find the z-score for 9.5. The center or the mean is 10. The standard deviation for samples is 0.33 of size 50. Don't divide by 2.3. If I was talking about one fish, you would divide by 2.3, but I'm talking about 50 fish. All right, so 9.5 minus 10 divided by 0.33 is negative 1.52. Actually, I'm going to use a couple more decimals. Negative 1.5152. All right, so again, that actually makes sense. Here's negative 1, so this is a little bit more than one standard deviation below the mean. Now all I got to do is grab my normal model, so second vars, number 2 for normal CDF. Now this time I'm starting down, so I'm going to start at a low value of negative 9999, and I'm going to go up to my z-score of negative 1.5152. And I'm going to go ahead and paste that in, and it's going to calculate the probability, and it's 6.49%, 0.0649. So again, that's fairly likely. That's definitely possible. That's not significant by any means. So if a sample did come back at 9.5 inches, I would not be surprised. I mean, that's fairly close to 10. It's only 1.5 standard deviations below, so that would be fairly likely. So again, sampling distributions give us a great picture of what samples are supposed to look like. And since like a huge part of statistics is looking at samples, you better believe this is pretty important. I do want to emphasize, though, that oftentimes the number one question that you're going to get on an AP stats test is to describe the sampling distribution. So when you are asked to describe the sampling distribution, please make sure you mention the center, you mention the spread, and you mention the shape. Now, let me just briefly recap all these. So for proportions, the center of all samples is the truth. For means, the center of all samples is the true mean. For standard deviation, that's the spread. For proportions, it's the square root of p times 1 minus p divided by n. And for means, it's the standard deviation of all, the entire population, divided by the square root of your sample size. And the shape is always going to be normal, provided that we meet that third condition. So for proportions, we need 10 successes and 10 failures or more. And for means, we need to be big enough, which means A, the population is already normal, which is awesome. If not, the central limit theorem says we do need our samples to be 30 or more for the sampling distribution to still be normal. So again, shape, center, spread, that's all that needs to be said. Even draw a little picture like I drew in the examples. They love that as well. But make sure you understand the basic idea of what we're doing here. We're not talking about populations. We're not talking about an individual sample. We're talking about a model of all possible samples and what they could look like. So that's a quick review of sampling distribution, and we even reviewed a little bit of probability in there as well. So hopefully everything made sense.